So what we're going to do is we're going to derive the Taylor series for, let's start with natural log of x around x equals 2. Okay, so f of x is actually natural log of x. So f of 2 is whatever ln of 2 is. Leave it in that form. Don't try to figure that out numerically. Only time you really should be figuring things out numerically is if you're programming something and trying to get a number estimate. Otherwise, try to leave it in this form. Then f prime of x is 1 over x, which I'll also write as x to the negative 1 just because the next derivatives will be a little easier that way. So f prime of 2 is 1 over 2. And then the and our second derivative, negative 1 over 2 squared. And again, don't simplify things like this because our goal is to find a pattern. So we don't need to do 2, 4, blah, blah. We just need to be able to say, okay, our expression is going to look like 2 to the something. So then if we keep going, fourth derivative. So I'm going to do the fourth and the fifth derivative just so we can really see the pattern. We notice some patterns emerging, like the powers of 2 and so on. But this one is kind of an outlier. We have this natural log of 2. So when we're making our Taylor series, the formula is the sum from n equals 0 to infinity of the nth derivative at x over n factorial x minus 2, not factorial, to the n. Right, like that. So this is our formula, but we're going to have trouble getting this first one, the 0th derivative or the 0th term, to kind of fit into this form. So I'm going to split it off and just worry about the rest of the stuff. So instead of doing our series like this, I'm going to just think of it as f of x over 0 factorial x minus 2 to the 0, and then do the sum from n equals 1 to infinity, the nth derivative of x over n factorial times x minus 2 to the n. So what I've done is I've just taken that first term and I've removed it and put it in front. I wrote this formula incorrectly though, so this one is supposed to be, this is supposed to be our 2, not our x. The x just goes here. That's my bad. This is the 2. This is the 2. So the point that we're expanding around goes inside the derivatives, thus us doing it here. So 2 is natural log of 2. 0 factorial is 1. So we have natural log of 2 over 1. And then anything to the 0 power, except for 0 or infinity. Most anything to the 0 power is also just 1. So that first term just boils down to natural log of 2. And then the rest of what we have here, we have the sum, n equals 1 to infinity. And this part, these parts are pretty self-explanatory. So really what we're trying to do is put something in for the nth derivative at 2 that shows the pattern and is in terms of n. So first thing we can see is we have an alternating thing going on here, where the first term is positive, the second term is negative. So when you have something alternating, you want to do -1 to a power. And I'm going to do -1 to the n plus 1. Because for this first one, n is equal to 1, but we want it positive. So if I did -1 to the n, like we've done for some other examples, or it's kind of similar to sign one, but if I did -1 to the n, then you're going to get the wrong signs. Yeah, but you're going to have the first one be negative and the next one be positive, so it's going to be wrong. So if you want to make the first, or the one corresponding to n equals 1 positive, you have to do -1 to the n plus 1, or -1 to the n minus 1, something like that, because an even power gives us a positive and an odd power gives us a negative. So that takes care of the alternating part. We still have another part in this numerator. And do you guys see what that other part is? What's the pattern? 1, 1, 2, 6, 24.
2 raised to the power n.
That's on the bottom. So on the bottom we have 2 raised to the power of n.
Yes.
And then we still have this all over n factorial. So yeah, we have a 2 raised to the power of n down here. But what about the top, the numerator? First term, we have essentially 0 factorial. For the second term, we have essentially 1 factorial. So we can call that n minus 1 factorial. So the other way to kind of know if you're getting yourself into a factorial situation, whenever we're doing derivatives where you're pulling a power down in front and the exponent here is increasing like this, then you can even see in a way that we're kind of constructing a factorial, in the sense that the first time you multiply by 1 in front when you take the exponent, the next time you're multiplying by 2 because the exponent is 2, then you're multiplying by 3, then by 4, then by 5. So that is what a factorial is, multiplying by consecutive numbers. So I mean, this comes from experience in doing these a lot, but when you, sometimes if you can't see the pattern immediately, it can help to think about how you were, getting those numbers in the first place. But it is good to be able to recognize the factorial pattern. So just seeing that it goes 1, 1, 2, 6, 24, 120, 120. I don't even know beyond that because it grows pretty fast. And then I have x minus 2. We can simplify this a little bit, and I don't expect you to simplify everything like crazy. I mean, especially here, like powers, exponents, don't simplify that. Like, that makes your life miserable. I am going to take this fraction and kind of and then we do n equals 1 to infinity of. So this is really the same thing as just saying we have -1 to the n plus 1 times n minus 1 factorial over 2 to the n times n factorial. So I'm just swirching my fractions. And then x minus 2 to the n. So it's a little simpler. We can do one further simplification. So let's just look at this little piece. If we have n minus 1 factorial over n factorial, what does this simplify down to? So n minus 1 factorial, this is saying, we have n minus 1 times n minus 2 all the way down to 1. And then n factorial means we have n times n minus 1 times n minus 2. If we look at what cancels here, saying the ones cancel is a little dumb, but the ones cancel, the 2's cancel, the 3's will cancel, it'll keep canceling all the way up. The n minus 3's cancel each other, n minus 2's cancel each other, and the n minus 1's cancel each other. So if we wrote out these factorials, everything cancels except for that n. So really this just becomes the same as 1 over n. So what I can do is, take this piece, the n minus 1 factorial and the n factorial, and make it a little nicer. So we get natural log of 2, sum from n equals 1 to infinity of, on the top we just have -1 to the n plus 1. And then on the bottom we just have n times 2 to the n, because the rest of the factorial stuff went away, x minus 2 to the n. And that is our Taylor series for this.